Yeah, so I'm going to be presenting on solving logical puzzles in DisCoCirc. So as a general overview of what the presentation is going to be like, to start with, I'll just go through what the framework is and kind of what ingredients we'll need to solve these logical puzzles, and then take us through an example and practice. So kind of from the start, we're working in a compact closed category. Objects are wires, morphisms are drawn as boxes, and we're reading from top to bottom. We can put things next to each other using the monoidal tensor of the category, and also compose things in sequence. There's states and effects, which are the morphisms without inputs or outputs. In particular, states are going to be used to represent word meaning, using sums or kind of superpositions of morphisms to kind of help differentiate different layers of diagrams. So we're kind of viewing each layer of a sum as a separate diagram, and we'll just sometimes write them like this in one single diagram as a notation point. The next thing we'll need is kind of copy spiders, or just spiders, which kind of abstracting away from all the like technical details of what they are, we can view them as effectively described in terms of a particular basis, and just kind of copying that specific basis. There's another element which isn't really part of our category, which we're going to call the duplicator. That's effectively going to just stand as a shorthand for doing the diagram above it twice. This is because in most of the kind of categories we'll be looking at, the copy spider doesn't copy everything, it just copies the basis it's defined on. So we kind of introduce this extra element as well. Another thing that we'll be using is negation. So here we're just kind of putting it in as an extra negation blob, because it's not really a linear operation, which is what we're kind of dealing with. So later on, well, if we're trying to implement it, we might kind of think about ways to like simplify the negation we're using so it actually works within our category, but we're not going to go into that here. And then the final thing is this kind of summation monoid. So we're going to be take elements which are kind of spread across the monoidal tensor and putting them into this into a sum, so kind of into a single wire. So it's kind of delicate how we need to define it, kind of to get a concrete version of it. But effectively, what we do is kind of add a dummy element into the types. So say if we imagine we're in rel, we'll just kind of add an extra element to the sets involved, so that can act as the unit. The cardinalities are okay when we're transferring from one to the other. So kind of building on from this, when we're expressing our problems, there's usually we might have a wire that kind of represent x's. We might need to think about, we might want to speak about only, say, the red x's as opposed to all x's. And so we're going to use these kind of fine psi morphisms to split the wire up. So kind of in the general sense, it's just splitting x into a kind of part of x's, of subsets of x kind of thing. And so we can express it in terms of the summation monoid and some encoding and decoding morphisms. So here we've represented the x as a green wire and then the pi of black, just to highlight the fact that we're also affecting the types, not just kind of the kind of elements that are flowing through the wires. So okay, so that kind of is all the elements we need, so we can now build up to kind of what DisCoCat. The first thing we'll need is grammar. So here we're going to just illustrate it with a kind of very simple pre-group grammar, but as we've kind of seen before, you can get more complex grammars or different sorts of grammars involved. So we're just picking some basic types, so a noun and sentence. We can label words with them, and then we add in left and right inverses for these types, so we can build up more complex words. So like a verb like loves, it requires a noun on either side, so we kind of built the type accordingly. And then to figure out if a sentence is grammatical, then we just kind of the kind of types with their inverses, making sure we respect the direction, and it's grammatical if there's a kind of dangling sentence wire left over. So this allows us to kind of check the grammar of the sentence. And then meaning comes in, as I said before, as states. So depending on what kind of underlying category we're in, they might be vectors, or maybe kind of sets if we're in rel. And then the grammar then, and the states is going to be dependent on their grammatical type. So that we can kind of wire them together according to the grammar. And then this gives us a way to create a sentence state out of the individual word states. And this is what kind of DiscoCat does. So we can then kind of compare sentences to each other because they all live in the same sentence space. So in some cases, we might also kind of hard code meaning of some words. So in this case, we've used dividers to define what is means. So in this case, it's kind of just intersecting ball and red to get a red ball, which is intuitively what we expect the sentence to mean. But this is all kind of not that helpful if we're trying to model a logical puzzle, because that usually comes as multiple sentences. So we need to see how they interact together. So that's when we move to DiscoCirc, which kind of stands for circuit. So we're now kind of plugging sentences together. And the kind of conceptual shift we needed here is having the types of the wires be the grammatical type, and now moving to having them be the kind of main characters or the objects that the text is talking about. So if we think of Alice in Wonderland, the character Alice, kind of her name occurs throughout it, but its meaning changes as we learn more about her adventures reading the text. So in this case, like Alex and the cat kind of go through the sentence and come out changed by the sentence itself. So we can then connect them to kind of get meaning that builds up as we read the text. Okay, so that's how we're going to compose things together. Here's a puzzle. How can we solve it? So the first step is to see that the kind of initial setup phase they were telling us, is telling us about what kind of properties we have and how they kind of fit together. So to do this, we're just going to use our psi-morphism to kind of combine the types together to get to T type. So here, blue is azerocyan, which is kind of combining them. Again, here, when they're all mutually exclusive, we can fit them all into one wire because we only want one value to ever be held at the end. But in the case of color and honesty, for example, we can put them together using the monoidal tensor because we want them to be kind of jointly held. And also as we're just going to color the honesty red throughout to distinguish it. So then, as kind of was alluded to, like spoken about yesterday, we also usually want correlations between the kind of possible properties things can have. So in this case, we know that blue natives lie. So the way we kind of structure this is using the phi to morph them to kind of split up the native into a kind of blue native and a red native branch. So that we can then apply a sentence to just the blue native branch. So if you can see my mouse, it's is the kind of applying sentence to the blue native, this being the blue native branch. And then we just kind of, because of how the summation monoid works, we need to project onto this kind of the unit of as well as an extra layer of the sum, just to preserve the red native so that it stays throughout, and we can merge it back together into a single native. So here we've kind of conditionally applied the natives lie to the blue native and left the red native alone. So the next kind of step of our puzzle is kind of knowing what the objects that we're going to be interested in are. So kind of in this case, we know that there's kind of 3 natives. So the way we kind of encode this is just by duplicating the generic native type 3 times. So in this case, in the more general case, if there's n things, then we just kind of copy things n times and then label each of them so we can then later on kind of know which thing we're talking about. And then finally, we're here told that each native is a different color. So this is kind of slightly different in that we're kind of having to apply the whole sentence in one go to just ensure the uniqueness of the colors. So we're going to use this morphism, which I'm calling the permutator, which basically takes m wires of the same type, each of which can take n different values, and then just kind of over, so each layer of the sum is just a single kind of permutation of these n values over the m wires, so that they're all unique, so that the kind of overall sum just gets us, well, gets us what we want, in that there's only ever one value present in each layer of the sum. So we get the uniqueness we want. And then finally, here we kind of, in the last bit, we kind of learned about the specific between the characters we have. So in this case, each of these, both of these constraints are kind of saying somebody says that someone else is something. So the kind of key word here is says. So we're going to kind of, we need to find a specific encoding for this that kind of helps us access the right sort of properties and get the meaning that we want. So intuitively, what we want is a kind of controlled negation operation that kind of affects the, affects the value z that we're applying to y, so that if x is honest, then we apply z to y, but if they're not, then we apply not z. So the way so we just kind of reverse engineer it a bit, and then we get kind of this big thing with the grammatical types all matching up. So if we simplify it, we can see that kind of yanking the wires and then merging the spiders, we'll get back to the kind of target form we wanted. So we can kind of just use that straight away. So that's kind of how we encode the whole puzzle. So this is what it looks like with everything kind of put together. So we can now think about kind of simplifying it and seeing how close this gets us to the answer. So in the first step, here we've kind of blocked off the top of the wires with kind of, in a sense, singleton states that kind of represent, so azure, cyan, red, etc. Because, so that we actually get the final state when we reduce the diagram. Otherwise, we could leave them open and they kind of give us a morphism that kind of takes as input some encoding of what azure means, and then will give us an answer based on that. But because it's all kind of self-contained, we can just give singleton sets there. So then simplifying it, we just kind of combine the layers together, and then here we get a kind of even superposition over all possible value assignments. The next step is then to apply the correlations. So here we've kind of, to make it all fit on one kind of slide, I've just ignored the other kind of projection onto the summation monoid unit here. But if we kind of look into more detail how it simplifies, you can see that when we kind of push the top sums through the phi, we then get these kind of diagonal terms, which will cancel out because of the way that the kind of plus was a kind of dummy element. So it kind of, these will come to zero, and we can kind of safely ignore the kind of parts of the diagram that we intuitively don't want, and then the rest is just applying the sentence to the blue natives and doing nothing to the red natives. So that's what we get, and then kind of merge it back together to get this. And so then applying the second correlation sentence, we'll get kind of state that kind of represents a generic native. So if they're either azure or cyan, they lie, but if they red, they tell the truth. So putting that back onto the rest of the diagram, we can see here. So then just kind of applying delta is just kind of copying the state so we have the right number of natives, and then we've indexed them with the kind of names we're given. The next step is just permute the colors, and then we apply the sentences. In this case, we've got it all kind of very nicely falling into place where we kind of know who Xavier is and who Yvette is directly. But in the case where, say, we might have a sentence saying the red native says Yvette is azure, then in that case, the way to get around it is to apply the phi morphism again to split each of our natives into a kind of red native and non-red native, and then apply the sentence to each of the red natives. So we'll have a kind of a more complicated sum that ends up kind of representing the meaning we want. So we can kind of, we're not restricted by the specific form we've initially chosen to kind of present the problem as. So then simplifying all of that stuff, we then find that we've actually just got the solution straight away. So in this case, Xavier is red, Vet is azure, and Zoe is cyan. And that kind of falls out from just having encoded the meaning of the logical puzzle. And we kind of don't really need to do any extra work to find the answer. So this is pretty cool. We can solve logical puzzles using DisCoCirc, but can we do anything else? And it turns out that actually what we've done is effectively construct a constraint satisfaction problem instance. And we can see that in the kind of the three separate stages of the problem. The first stage was identifying what the kind of properties we had, and so this kind of corresponds to setting the domains of the CSP. And then the next step was identifying which is the variables, and then the final kind of actual puzzle section were the constraints. So it's a kind of, can potentially use it as a method to translate just textual based encodings to the kind of CSP. And also maybe looking more towards real world problems, if we had a kind of prior encoding of the kind of what our types were. So if we kind of knew that bananas were kind of had a color and a taste and so on, as we saw yesterday, be able to apply these directly to then look at reading comprehension or something like that, where we're relying on background knowledge, and it's not all given to us as part of the problem. So then looking at complexity, the kind of finding the encoding is just a case of basically finding grammatical wirings, and that's attractable. In this case, we've also done some extra work in identifying the kind of different parts of the problem, because we're encoding those slightly differently. But it seems, at least on the face of it, that we should be able to do a lot of this work grammatically. So for example, the distinction between kind of the general case and the specific cases where I'm applying the objects can kind of be seen in terms of whether we're using a plural or not. So cats in general versus that cat or the cat. So it can be done there. So if we use maybe a more sophisticated grammar than we've kind of presented here. But obviously CSPs are NP hard, so finding the actual solution once we have the encoding isn't, well, is limited by this. So, well, that's one way of solving them, but obviously other people have come up with different ways. So the kind of standard way is to encode the text of the problem as a kind of first order logic formula, usually going via like modal logic. And then kind of throwing the whole thing at a SAT solver to get the answer. And interestingly for humans, there's kind of a different perspective where we're kind of, we draw out a Euler diagram for each of the sentences and then use a kind of associated calculus to combine them all into a final diagram, which we can then kind of read the answer from. And in this case, method here seems to be kind of doing a bit of both, in that we are encoding each separate sentence independently and then kind of computing a final answer from the kind of encodings of the separate sentence by simplifying our diagram. But we've also reached a kind of logical encoding kind of implicitly from just encoding the diagram text, the puzzle text. So we can kind of, in some sense, convert back. So, for example, we've included negation kind of independently, but then we've also got the spider kind of acting a bit like an and then the different layers of the sun kind of acting a bit as a kind of or. So in that sense, we've kind of still captured the logical form within the diagram. So the kind of conclusions to be drawn is that we can solve logical puzzles by kind of encoding their meaning directly rather than extract the logical form explicitly. But for now, at least, it requires a bit of manual labor in identifying the different components of the problem so that we can encode them appropriately. But potentially we can reduce that by focusing more on how the grammar works. Yeah, thank you for listening.
Thank you.